Okay, so in this lesson we're going to talk about differential equations. You know a little bit about differential equations already from previous work in calculus. This is section 9.1, 9.2. We're going to talk about these equations, and this should be familiar to you at this point because we've talked a lot about antiderivatives already, and we've talked a lot about integrals already. So this is where we first introduced the antiderivative, but first of all, what is a differential equation is what we have to understand. When we talk about differential equations, what we're talking about are equations that have derivatives in them, and they're also sort of equated or explained by, some original input variable. So these are examples of differential equations where it has some value and its derivative in the equation. So this is straight from your textbook. It says this: many of the general laws of nature find their most useful form in equations that involve rates of change. These equations are called differential equations, right? So if we take a look at this, equations that involve rates of change. So we know that rates of change are what derivatives are, right? So this is a rate of change. That's the derivative of y with respect to x, or how y is changing with respect to x, its input variable, right? So that is a derivative. That's a rate of change. And obviously, a rate of change will depend upon its original state, or upon its the variables that we're inputting, right? So it has to do with plain old x. Okay, so it's the derivative of the function, and it has to do with x. Okay, or here's the derivative of velocity. Okay, and here we have just a value, so it's not dependent upon another variable, right? It's just a constant, but yet we have the derivative in an equation with other values. Okay, so these equations are called differential equations because they contain functions and their differential quotients. So an equation, you could write an equation, okay, containing a derivative. A derivative, and either the input variable or some constant, at least, as we saw in equation 2 there. All right. Now the question begs to be asked here: if I have d over dx of y, right, the derivative of y, if I know that that's 2x, then what is y? Now we know how to solve that. This is almost too easy at this point, right? You know that if y prime is 2x and I'm looking for y, what we're looking for is the antiderivative, right? Or we're looking for the integral. So we have to integrate to get y. Because remember, this is same as f prime of x is 2x. And so what is f of x? Right? The antiderivative. So what would it be here? How do we find the antiderivative of 2x? We add 1 to the exponent here, so that's going to make it a 2, and then I divide whatever's in front by that new exponent, and that's 2 over 2, which is just 1. So if 2x is the antiderivative, then x squared is the original function, right? Now, what have we talked about up to this point? What have we always had to do if we're talking about a general antiderivative right here? A general antiderivative. We always have to do what? Plus c, okay? Plus c. So up to this point, what we've been saying is that the original function is x squared, but we're not exactly sure if this parabola, x squared, lies at the origin, or if it lies at x equals 2, or if it lies at x equals -1. Okay? Down here like this, see? We're not really sure, but we know that the derivative would form what looks like, in this case, a parabola, but it may be shifted up or down some ways, and we don't know, what this constant would be. Okay, so when we're talking about differential equations, what we're going to specifically talk about today is differential equations with initial conditions. So that's what 9.2 is. All right, so let's just kind of shift from here. Okay, so 9.2 is this. So, differential equations with initial conditions, a question that might be asked is this. Given the derivative of y is 6x squared plus 6x, now that's the expression for the derivative, right? That would be the expression for the slope of a tangent line at any value x, that's the expression. And what we're asked for is to find the function, so that is y equals f, capital F of x, so the antiderivative, right, or the integral, that passes through -1, 0. And this is the important part. We've never been given this before. This is what you call your initial condition. Okay? And this is going to help us determine what C is. All right? So with the initial condition of the fact that, right here, that the function passes through this point, we can calculate C and give the particular antiderivative, not the general one. We can give the particular integral or antiderivative, okay? And I'll show you how to do that. It's basically just one more step from integrating or finding the antiderivative. It's really pretty easy, and I'll explain how how plus c. We don't know which graph it is, and then we're given this condition. Well, now we can find a constant that allows the function to pass through this. Okay, so if we're going to find f of x here, here's our solution now. Okay, if we're going to find f of x, that means we have to find the antiderivative of this. Right? We basically want to integrate this. We're going to integrate both sides with respect to x, right? Okay. So, what do? What's the integral, or the antiderivative of 6x squared? I'm going to bump this up to a 3 and then divide by 3, right? So it's going to be what? 2x cubed plus what? 3x squared. Okay, is that agreed? Now, normally this would be plus c, and that's the general antiderivative. We're done. But now what we're going to do is we're going to find out, hey, what is this c? And the connection is right here with this initial condition. Okay. All right. So the general antiderivative means that I know what the function looks like. It looks like this. Okay. Y equals 2x cubed plus 3x. That's the shape of it, okay? Because that equation for the derivative, it works. If I'm going to plug in 0, I'm going to get a derivative that matches with this, pretty close to 0 right there, right? For that original function, which makes sense. I put 0 in there. Okay, 0, or for the original question right here, I put 0 in there. I get a derivative of 0, right? If I put 1 in here, that's 6 plus 6. So at x equals 1, I should have a derivative of pretty close to 12. Well, here's x equals 1. So on this, look at that, it's really steep. You see that? The tangent line slope would be pretty steep, pretty close to 12. That makes sense? So that differential equation says, hey, if I've got an x value, I plug it in, I solve, and then I've got my derivative, not my y value, but my derivative. I've got the value of the derivative. So this works. This is the equation. Okay, that's the original function of that would yield a derivative with that expression. The only problem is that the plus c means that we don't know whether, if it's plus 0, as in this black line right here, or is it minus 1, or is it minus 2, or 3, or 4, or 1700. We don't know. We don't know which is the exact function. But when we're given the initial conditions, okay, there's the x value, -1, right? Go back to our question, which, disappeared, but there it is now. So our original question Here's negative 1, 0. See that? So the original function that we are going to find has to go through that point. And so, you know, we go back there, then here's the point. So guess what? This red function is the actual one we're looking for. Now, how do we know it's minus 1 here? How do we know that c is minus 1? Well, here's where it actually gets pretty easy. Okay. Here is the equation for the actual function. If I know that x equals negative 1 and y equals 0, I simply put in those values. So f of x is 0. That equals 2 times the x value is negative 1. And I'm going to cube that. Plus 3 times negative 1. And I'm going to square that. And then I'm going to add c. And I'm going to now solve for c. Okay? Put in x, y, solve for c. So I get 0 equals negative 2 plus 3 plus c. Add 2, well, negative 2 plus 3 is 1. So c equals, over here, negative 1. And now we can say that our actual value for this function, the actual function, is 2x cubed plus 3x squared minus 1. That is the actual function because we were given these initial conditions. And so if we're not given initial conditions, we're actually looking for a general antiderivative. You would add plus c. If we're given initial conditions, we take that final step to find the actual function. Got it? Any questions? All right, so if we're given a differential equation to find the equation of the original, the mother function, right, then we integrate, right? And if we want to find the actual mother function and not just some general mother function, then we can use initial conditions if we're given it, okay? Right? Yes, I just explained the idea of the mother function to my pre-calculus 30 class today, and we had good fun with it, of course, but, you know, the mother function is the one that gives birth to all the little baby functions, right? Okay, so here we go, the original function. Okay, so there you go. That's pretty much the lesson on finding particular antiderivatives given initial conditions and working a little bit with differential equations. So it is important to note here that this lesson too is first order differential equations. So I'm going to add that right here, first order, which basically means this is the first derivative here always, first derivative, okay? Gets a little trickier if it's not first order, but this is how we do it. We just take the antiderivative, we integrate once, plug in our initial conditions, and then we're good to go, okay? First order.